Okay, so thanks very much for the introduction, and let me add a general comment that NVIDIA, represented by the three speakers here, myself, Mark Harris, and Lars Nyland, we're really honored to be invited and included in this. It's really exciting for us to see the sort of self-organization of conferences among domain experts, among the sciences and the engineering disciplines, of sort of self-organizing conferences devoted to the use of platforms that we make toward their discipline. That's exactly the kind of thing, the kind of grassroots effort that we hope will happen, that we're excited. We're very honored to be included and allowed to talk here, and we'll try to repay that honor by not deluging you with marketing information. You can recognize the slides that came somewhere from a marketing deck in my talk, because they have like more than 2 colors or 3 colors, and they have pictures, figures. We are all technical people, and we will be most comfortable answering technical questions. My name is David Luebke. I am in a research group at NVIDIA. My background is in real-time rendering technology and general-purpose computing on GPUs, and I'll talk a little bit about that, of course, as I get going. My talk here is intended to be sort of a broad introduction to GPU computing and why we think that it's exciting, not just in terms of sort of raw numbers, horsepower and flops, but I'm going to try to sort of pose a slightly larger picture first about how what to us is exciting about GPU computing is that it's really this sort of democratization, a revival and democratization of parallel computing. So, parallel computing is an interesting discipline because it had this real golden age. In the 1980s and early 90s, there was an enormous interest in both on the academic and the commercial side in real sort of hardcore data parallel computing. You had machines being built like connection machines and Crays and MASPAR, all kinds of exotic, expensive, but incredibly powerful for their time computers, and accessible only to a very few people. They were, there was this collection of acolytes. Many of the people in this room have probably touched these machines or programmed for them. The world at large has not, and that's a point I'll return to. The other sort of part of this golden age was all of the study into the algorithms and the programming models, the ways to reason about complexity on parallel computers, and how to actually solve problems. How do you harness the horsepower of a data parallel computer to solve sorting or all kinds of sort of basic computational primitives. And so parallel algorithmic models were developed, parallel complexity theory techniques were developed, parallel architectures for machines were developed. And then it all kind of went away. There followed what I'll call sort of humorously a dark age of parallel computing. What happened was that the impact of these exotic, expensive, powerful machines was limited. There were hundreds of connection machines sold. There were a couple of hundred of MASPARs sold. These were really interesting, fascinating machines to program for, but there just weren't many of them, and not many people could touch them. In the meantime, the sort of steady grind of commodity technology was making standard PCs that you buy off the shelf at Best Buy. They were evolving into incredibly powerful machines, and people realized that you could lash together these machines and to outperform even the most exotic supercomputers. And so Beowulf and Legion and what's evolved into sort of a field known as grid computing, sort of federating large clusters and possibly geographically distributed clusters of computers was really the next wave. And this is what attention turned to academically, both on the users, domain scientists who just wanted to solve their problems, and even the computer scientists who were trying to design these systems in the first place. So this is the era of distributed computing, and the lessons learned there are by no means irrelevant. They're very important, and we will continue to have techniques like OpenMP and MPI and so forth. But what's interesting to happen is that sort of all this excitement surrounding data parallel computing evaporated. It was essentially steamrolled from behind or gobbled up from underneath by the inexorable advance of commodity technology. The sheer economies of scale that companies like Intel could innovate at just obliterated the exotic supercomputers for the most part. And so what's interesting, if you think about GPU computing in this realm, and this is an inside I/O to my co-speaker Mark Harris, you can think about GPU computing as a sort of democratization. So we had the golden age, the dark age. Now we fast forward, quite a while. Now parallel computing becomes this democratic technology because we've sold roughly 40 million machines that support this CUDA platform that we'll spend a large part of the weekend talking about. And CUDA, as you'll see, is a true data parallel language. It's a true data parallel platform, hardware and software co-designed to do, honest to God, raw data parallel computation. And this means that all of a sudden, data parallel supercomputers are everywhere. We sold more in our first quarter than all of the Crays and connection machines and probably SP2s put together. I mean, they're just and what's interesting about this is not just that it's accessible and that you can go and buy for $200 a data parallel supercomputer of sorts. Is that people are innovating in it, and this is sort of a call to the academic community here. We are already seeing new ways to sort better. Okay, sorting is a pretty well-studied problem, but the fact is that there's 40 million GPUs out there. We're seeing new approaches to parallel sort starting to emerge. We're starting to innovate in the space of data parallel algorithms and data structures and how you handle these things. And what's exciting about this is that parallel computing is all of a sudden riding this wave of commodity technology instead of getting inundated and swamped by it. As computer scientists, as scientists, as domain scientists, you should be deeply skeptical of anybody who says, I've invented a new machine that will solve your problems. That's a very hard thing to do because then you have to make millions of those machines to have the kind of economies of scale that will make them cost effective. And that's what's exciting about GPU computing is there was already a market for massively parallel computers. It was called computer graphics and it was called video games, frankly. And it turns out that the kind of problems that companies like NVIDIA had to solve to solve the computer graphics problem, to make really efficient computer graphics, are exactly, or at least closely, isomorphic to the kind of problems you need to solve to do, data parallel computing in general. And so, as I'll talk about, with sprinkling of a little bit of sort of architectural sugar into the machine, we were able to support broadly general purpose computing, and that's opening whole new markets for us, which of course we're excited about, and whole new opportunities for science and engineering. This is the other part of the pitch. Computing is not just a good idea; it's the law. I mean, it's the only way you're going to gain performance. To first order, computers don't get faster anymore; they just get wider, right? The industry as a whole, the CPU industry as a whole, has completely shifted away from making processors faster. All they can do is make more of them on a single die, and it's interesting because a lot of people haven't gotten this memo yet, and not grokked the implication of that, which is that if you write something and it's not fast enough on a given set of data, it's not going to be fast enough. It's not going to get faster. You can't just wait a couple years to tackle more problems unless you remap your algorithm to be parallel, to take advantage of the increasing parallel resources that are available to you. And there's different kinds of parallel. There's data parallel. There's task parallel. Of all of these, I'd argue that data parallel computing is the most scalable solution. So the problem is dealing with huge data or huge simulations. Data parallel computing is the right match for you. And that's really what GPU computing with our platform called CUDA is all about. It's a scalable data parallel platform that is written in a familiar environment, C. Okay, this is especially important for business interests. You can't convince a business to write something in a language they've never heard of. They really have to build on their existing competencies, existing strengths. And so you can write in the C /C++ language family. You can write massively data parallel code. The motivation, the fact that you're all here means, presumably you have some motivation to at least, go somewhere and hear about GPU computing. This is a collection of applications that were not written by NVIDIA. We did not write these, and we didn't exactly even collaborate in making them faster, although you could take exception to a couple of these. But these are applications that are written by other people for their own purposes. This is an FTTD simulation of electromagnetic fields for things like cell phone safety. This is just actually a teaching code written in MATLAB for a fluid dynamics course that we replaced some of the MATLAB calls now are just basically plugins that call out to CUDA, and so you get a 15x speed up. This is an in-body simulation, I think, from Illinois. This is gene sequencing, basically pattern matching. This is an MRI. This is MRI reconstruction using new orbits of the sensors. This is VMD, something you'll hear about in maybe I think the very next talk, molecular dynamics. So, so in some sense, we don't need to motivate this much more. I'm not going to I'm going to sort of soft pedal the motivation because this is it. The reason to do this is that real people doing real problems, not just sort of marketing benchmarks, can get real, honest to God, important speed ups on their codes by using GPUs. And of course, there'll be tons of posters and talks about this. So I can sort of soft pedal the fact that GPUs are fast. Presumably you buy that. That they're fast, they have roughly 10 times CPU bandwidth, roughly 10 times CPU computation, and it turns out a better programming model for utilizing all of that power. And so, peak numbers, they're impressive. Just sort of the 472 gigaflops for our very fastest chip, the 8800 Ultra, 86 gigabytes per second of bandwidth on our high-performance computing chip, the Tesla class. And more important is that there are actually useful applications, not just sort of micro benchmarks, that can achieve that can achieve results almost half of that. So 240 gigaflops on a real application on a single chip is just unheard of. That's just awesome. That works out to 12 billion interactions per second. So will be talks and posters about this, as I say. So here's an obligatory slide. Anytime you talk about GPU computing, you show a slide like this. The point here is not so much the numbers, and in fact this is slightly inaccurate because advances of the compiler toolchain have pushed this up into the 470 range. But the point is the shape of the curves. Okay, the GPUs are getting faster than CPUs are getting faster, and the reason is that they're better suited to take advantage of this sort of new Moore's law, this increase in parallelism rather than increase in clock speed. And they have been better suited to take advantage of that for quite a while. So this is they're not only fast, they're getting faster, even differentially. A few examples of specific numbers and speed ups. There are a couple of kind of weird applications that happen to map really abnormally perfectly to the GPU, and you can get tremendous speed ups. Often because they map well to the architecture, and they happen to use some little piece of hardware that some particular computation that we've accelerated in hardware, like reciprocal square root or sine, cosine. These are things you use in graphics, and so there's little architectural boxcars in there whose job it is to do fast sine and cosine computations. That's the reason for a 200x speed up. But even fairly standard codes get 10 to 20x is expected, and 50x you'll get occasionally. You can do even better on real applications, as I showed. You might legitimately ask why they're so fast. I sort of said vague words about they're better suited for using more transistors. What it comes down to is that GPUs are all about math-intensive data parallel computation. That is what you do in graphics, it turns out. And so, GPUs are designed to devote almost all of their transistors to computation, the flops, rather than to data caching and flow control. For those of you with a computer architectural bent, I would phrase it as CPUs mask latency with caching, latency to main memory with caches, GPUs mask latency with threads, with other pieces of computation that can go on concurrently. And so this is not only a good design, but it is a commodity industry. As I said, we make millions of these, and so we have economies of scale behind us. We can fab tremendous numbers of chips and drive down the individual cost. And it's a competitive industry, an extremely competitive industry. There's this very healthy competition between NVIDIA and ATI, and Intel is entering the fray. That is fueling the innovations. There's economic motivation to make them faster at the high end, and there's commodity technology wave to make it cheaper because we also sell these things at the low end. And so that's my sort of pitch. Why do you care about GPU computing in sort of a broad sense? It is a revival of data parallel computing, and thus it is for lack of a less overused word, it is a paradigm shift so actually it's a shift back to thinking about really aggressively data parallel computing. I'm going to talk briefly, and I will fly through this part a little bit, so forgive me if I go a little fast here. I want to talk briefly about what is different about what we're talking about with GPU computing versus GPGPU, which is the phrase that Mark coined and that has been used for years to describe general purpose computing on graphics processors. at NVIDIA, we've sort of made this distinction. It's somewhat a marketing decision, but we've made this distinction between GPGPU as sort of a good label for what we did before, which was basically try to exploit this horsepower, all this computational horsepower, by tricking the graphics pipeline into doing the work for you. So you would you would draw pixels on the screen to invoke computation, and you would bind your, you would take your data and pretend that it was an image. You would map it into the red, green, blue fields of an image and bind that as a texture map that would be accessed by those pixels, this kind of thing. It was very, very exciting to those of us in the field, and Mark and I are both people who worked on this field early on from the computer graphics side. It was very exciting because we could see the potential, but it was very arcane. It was very hard to explain to people why, anybody outside of computer graphics, what these terms even meant, and they had no intuition for how they should be used. And so, tough learning curve, and plus we were still basically tricking the graphics API into doing general purpose computation, and there's overhead in the graphics API. It was designed to do graphics fast, not to do in-body simulation or radio astronomy. There were also constraints on where you could put memory and how you could access that memory. That again were basically, they didn't have to be there, but they were inherited from the graphics pipeline. And a more subtle point is that you would end up needing to use many passes. You would have to render the same thing over and over again to sort of advance the computation each step. And this tended to drive up bandwidth computation. So the solution to this problem is what we're calling, to distinguish it, GPU computing. And our particular platform for GPU computing is called CUDA. CUDA is the Compute Unified Driver Architecture. What this really means is this is a co-designed hardware and software platform. So there is a chip that's called G80, that's its code name internally at NVIDIA, and G80 was designed from the ground up to include support for general purpose computing. And there's a bunch of things in there, I've listed them here, that you need to do really good GPU computing in the general purpose case that you don't need for graphics. You need the ability to launch threads without pretending that they're pixels. You need the ability for a thread to read and write anywhere in memory as opposed to just inheriting some interpolated attributes from a polygon and writing to a particular pixel. I'll talk about these in a second. The other half of this effort was this big software effort to build a stack that lets you program the GPU in C as opposed to some graphics language like CG or OpenGL shading language or so forth. And the real clever design here is a scalable data parallel execution memory model. And I'll talk about that in my second talk today, which is sort of an introduction to CUDA. But the upshot is that it's C with a minimal set of extensions that expose sort of the power of being able to do massively parallel computation. This is what GPGPU looked like. You would do this very abstruse sort of collection of things. You would have to specify vertices of a triangle and how those vertices mapped onto the screen, and then a process called rasterization takes takes the triangle and turns it into the pixels, and then each pixel would potentially access some memory called texture maps and write the result into a particular pixel. It was a very complicated set of steps to go through. And this is how you would sort of reuse that graphics pipeline to do, say, A plus B, to add two matrices. I won't even go through the steps again. It's clearly arcane and abstruse and difficult, actually, even to even conceptualize for people who didn't sort of come through from this field. So I want to talk briefly about the hardware additions to the GPU to make it more suitable, because these concepts will come up again as we talk about CUDA later in the weekend. So this is sort of building a better pixel is what I call this. This is what the workhorse of the graphics processor, the pixel processors, what they look like in previous generation GPUs. You have all those steps that I talked about, and then in the pixel processors, you can run a pixel program, which takes some input registers. These are basically inherited from the vertices of the triangle that the pixel is part of, and it has read-only access to images called texture maps that it can use that are used normally to sort of slap an image onto a triangle to make it look like brick or wood or alien skin or whatever. There are some constants that sort of decide what kind of where are the lights in this setting? What is the I can't even think what is the matrix by which the vertices should get multiplied by and so forth. And there's also read-only, and there's a collection of temporary registers. But the biggest restriction overall was that in the end, this pixel was going to produce a single data value. It was going to write a piece of data to a given pixel in memory. And that meant it was writing a color. And that color had red, green, blue, alpha, In fact, you could write 4 pixels simultaneously, and the same pixel in 4 different layers. So you could write a total of 16 numbers to memory. That was the output of your program. This is really limiting. It forces you into this sort of functional programming model where here's this slot that your data is going to go in, and now you have to figure out the function that sort of sits above that slot and puts the right data there. That's difficult for many programmers to conceptualize. And there's other problems. Textures turned out to have limits on how big they could be, so the amount of data you could feed into this was limited and had to be two-dimensional to get optimal performance, and so forth. I won't dwell on this slide. So what the NVIDIA architects did to sort of address these problems is a series of changes, of additions, really. How am I doing for time? I don't have a clock. What? 13. Oh, I think I said 30. I said, oh. Okay. So this is the pixel that I just talked about, and let's talk about how we sort of make it better. So the first thing is to stop thinking of these as pixels in the first place. Okay. What the GPU is really doing is when it's processing thousands of pixels simultaneously, is it's actually running thousands of threads. I mean, that's what a general computer scientist would call them. You've got thousands of threads, each running a fairly simple, small program. And so instead of having to invoke these threads by drawing pixels on the screen, just let the user directly invoke threads. And we'll talk about the details of how this is done in the first CUDA talk. But this is we're going to run a bunch of programs. Each one is a separate thread of execution. That means, and because they're separate threads, they can diverge. They can do different things. They can have an if statement, and one can go left and one can go right. This kind of thing. And they need to be more general purpose than graphics threads. It turns out they need to. Graphics threads typically only have 1,000 instructions or less, but people need to write real programs that have millions of instructions. They need to have integer instructions. Graphics didn't need integers, just floats and so forth. You need to be able to do looping and branching and so forth. The next thing is, instead of being restricted to this setting where you can only write this particular little chunk of data, give these threads full read-write access to the memory. So there's this notion of global memory in CUDA, which is just all of the memory that's on the GPU. It's like 1.5 gigabytes in our current high-end cards. And so now threads can read and write global memory, and they can scatter, they can gather, they no longer have this utter restriction. Some memory is read-only, and the output is write-only to a single place. That restriction goes away. And there's pointers and so forth. And finally, this is the big one. There's the addition of this thing that's called the parallel data cache. In CUDA terms, it's called shared memory. What this really is a small chunk of memory on the chip that's extremely fast that is shared by a group of threads, what we call a block of threads. So a bunch of threads can share this small parallel data cache, and they can use it as a place to stage memory on chip. Or they can use it as a place to intercommunicate. So one thread can compute something and then use shared memory to share it with the whole block of threads. And this is a critical addition, it turns out. I mean, this was critical. Rewrite to global memory was brutally important, but this parallel data cache was also extremely important because that gives us the ability to let all these threads, what used to be pixels, intercommunicate, and that turns out to be enormously useful. Well, that's easier to answer now that I have this slide. So we'll talk in detail, believe me, about this. But the short answer is that there are 16 what we call multiprocessors, each of which has 8 lanes and runs 32 wide groups of threads. And the parallel data cache, each of them has its own parallel data cache of 16 kilobytes. So it's small. It's really a staging area. It's not a cache. It's not a traditional cache. That's why we gave it a different name. It's really a small data cache. And the fact that it's parallel is referring to the fact that there's many of them, but that that many threads can access this cache at once. That is the GPU architecture, by the way. The thing to notice is that in the end, there's 128 processors operating in parallel. What's not shown here, and what we'll get to again later in more detail, is that there are many more threads than that. There are up to 12,000 threads in flight at any one time in this machine, and so it's truly sort of a massively parallel machine in that sense. My last slide about the architecture sort of zooms in on one of those units. These processors, these 128 processors, each provides 1.3 well, they're scaled at 1.35 gigahertz. They've got full-blown floating point. What's interesting is that these are each running a separate thread. These are each, they're independent. This is not like, those of you who use SSE instructions in Intel processors, this is not like that. This is not a wide register. These are separate independent threads that can do different things. They can diverge, converge, and so forth. And they share that small 16 kilobytes of memory. Very fast memory. It's sort of register speed, so it's extremely fast. One of the last points I want to make is that one of the things that you are legitimately, you should be legitimately concerned about is that in the past GPUs have not had strict IEEE floating point adherence. It wasn't just not necessary for graphics. This is another one of the things you just don't need. You don't need perfect. You don't need all of the varieties of IEEE floating point to do graphics for video games. But you do need it for general purpose computing. And so people always ask us, do GPUs do real floating point? This answer, I don't have time to go through this slide, of course, but this slide, and there's collections like this, and there's tables like this in the CUDA programming guide, is intended to sort of to address that kind of thoroughly. We support IEEE 754 precision. That is a vast, complicated spec and no vendor perfectly satisfies everything in it. But we're sort of comparable to what else is out there. If you look, for example, D-norms, we do not have D-norms. Which are very, 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 very small numbers. Neither does the cell. Regular chips, it's supported, but in fact, it'll cost you thousands and thousands of cycles. If your code ever does that, it'll slow down to a crawl, and so it's only supported in sort of the loosest sense. We do have not a numbers and infinity support. We don't have a hardware square root, but we do have reciprocal square roots that are very fast. And for things like in-body, that's a good sort of beginning of an iteration and so forth. The upshot, sort of the message we try to get across here is that GPU floating point is, IEEE 754. It's comparable to other accelerators like SSE and Cell and so forth. It's more precise in some ways, and it's less precise in other ways. But one thing we can claim is that it's getting dramatically better every generation. And our goal really is to be sort of best in class in 2008. The upcoming generations of chips should be truly world class. The best support of IEEE floating point out there. These are some performance numbers. I don't think I need to dwell on these. They're actually on the slide earlier. The point to make is that having this parallel data cache, it turns out to be important for many kinds of computation. It's very important to leverage that ability to stage work and to share work among threads. Of course, it's good to have very high bandwidth to memory, which we do. It's good to have a large number of floating point operations per second available, which we do. And some applications can actually use these sort of custom hardware intrinsics that are very, very fast, slightly lower precision implementations of sine and cosine and reciprocal square root and so forth. All the benchmarks that I've showed, by the way of bar graphs of different speedups and so forth. That's all compiled code. There's no hand-tuned assembly. We don't do that when we're marketing because nobody can achieve that but us, and so it's not really fair. So these are compiled code from CUDA, from this from this extension to C called CUDA. I'd be remiss to my corporate duty if I didn't at least throw up. Here's the marketing slide. You notice it's got a picture, color scheme. That we actually sell these. We've just recently started selling these specifically for high performance computing. And this is a line of graphics-free GPU, graphics processing units without the graphics. There's no DVI. There's no cables leaving these boxes to drive monitors. It's called Tesla, and we sell 3 different varieties: a card that's just an accelerator card that goes in your workstation, a desk side thing that looks like it might be the size of a refrigerator, but it's about the size of a shoebox. That's basically 2 cards, an independent power and cooling supply. So it's like a desk side accelerator, about a teraflop of performance, and a 1U 4 GPU unit, which is 2 teraflops in a single rack unit. So this is obviously for stacking huge amounts of compute power. Oh, and there they are again, as I said.
What do they cost?
So I'm embarrassed to say I don't know exactly. I think this is I'm really not a marketing guy, honest. I do know that at supercomputing in a couple days we will be taking orders. So I want to say, Kevin, you just got a quote. What was that quote for? But which one? Okay, so the one in the center, the MSRP is $10,000. $10,000 for 2 teraflops in 1U, roughly.
I don't know if that's MSRP. It might be academic.
No, that's MSRP. Academic discount would presumably be lower than that, but even though I'm involved in that decision, I have no idea what the academic discount will be. We haven't reached that stage.
Do you have any watts per flop figures?
Watts per flop. You asked about that too. It was like 500 watts average for that thing. What you're getting at is performance per watt as a key differentiating metric. This is an advantage to us. We do very well with flops per watt. I don't know that. I guess we could do the division. I mean, the peak of that thing is roughly 2 teraflops, and it's roughly 500 watts sustained draw. So that's better than like a CPU, for example, or a cell, I believe.
Yeah, I know the GPUs are better, but
again, a marketing person would have that slide in their back pocket. I don't. I just know that's good for us, and that's a statistic we like because it plays to our advantage. We're sort of more architecturally efficient on these broad dense data parallel problems. Okay, so I'm concluding here. So what is the future of GPUs? Are we going to just keep making GPUs for video games and this high performance computing stuff is a sideline? No, definitely not. I mean, for us, this is the next big market. It's potentially much bigger than video games. We're extremely excited about it. We want CUDA to be everywhere. We want to see it in science. We want to see it in automobiles. We want to see it in cell phones. We really are. We see this as the thing that springboards us from a company that makes graphics chips to a company that makes computer chips. First-class computational devices. And it's exciting because GPU computing. You're talking about 50 or 100x speedup on some real applications that people will talk about today. That changes what you can do in the science, right? That changes the approach you can take in science and engineering. And so that's really exciting. We hope you find it exciting. I think the existence of this conference is a sign that it's exciting. From our part, these new applications drive the future of GPUs and GPU computing. I mean, knowing what's important, as you use GPUs, you will discover things that are missing, things that you need to be better. Performance of this needs to be better relative to that. That drives us. And of course, it also drives the market. It drives the hunger for more performance and more GPUs, and that's why we're here. And we're excited. We're very excited about new domains like simulation and physics. AstroGPU is a perfect example. And if you're curious what else we're excited about, we're also extremely excited about things like vision processing, acoustic processing, embedded applications of what you could do with GPUs. If you're wondering sort of what else we're going to do besides sort of traditional high-performance computing, it's really interesting. Vision, speech, these are domains that should map very, very well to computer graphics. And again, enabling new features, new ways of interacting with the world around us. You have speech processing and vision processing and embedded GPUs. So, concluding, the GPUs are the new massively data parallel computers. It is by far, by orders of magnitude, the most successful data parallel processor ever built. And CUDA lets you program the thing accessibly. You can buy a $200 card and start programming a data parallel machine. And it's a powerful paradigm. As you'll see, it enables a broad variety of data parallel algorithms. Mark will talk specifically about that. There's also a ton of scope left for innovation. I mean, we're scratching the surface. And now, again, we've got this democratization. Everybody can go and do this. It's not a supercomputer you submit jobs to. It's sitting on your desk. There's new ideas in how to do parallel computing and how to do science are starting to emerge from the woodwork. So my last sort of motivational, hopefully, call is start contributing. This is an exciting time. So we're excited to be here. Thanks again for your talk, for having me here. And is there time for questions? Probably not.
We took the questions.